All right, now we're going to talk about atomic mass. Now you might be saying to yourself, didn't we just talk about atomic mass? And the answer is no, we talked about mass number. They are different. And these are the two most confused concepts of each other. Atomic mass versus mass number. It's because they have the word mass in it. So it is very important that you understand the difference between the two. They are kind of the same, but not really. Okay? The mass number, remember, is your protons plus your neutrons. Okay? The atomic mass is the average of it's the weighted average of all the naturally occurring isotopes of the element. Okay? Which I will explain in a second. Okay? The atomic mass unit, I'm not going to talk too much about. It's basically just the unit that we use to, I'll describe the mass of these atoms. Okay? But really, it's the atomic mass that we're looking at on this page. Okay, so what's the difference between mass number and atomic mass? All right, if you look on the next slide, you can see right here, let's just look at carbon since that's what we're talking about. See, carbon has this number at the bottom, this 12.011. Okay, that's the number we're talking about. We're talking about how do we get this number? We've talked about 12, carbon 13, carbon 14, but we have not talked about what this 12.011 is, and that's the atomic mass, not the mass number. The mass number, you've got 3 carbons. You have a carbon 12, that's the mass number. Carbon 13, that's a mass number. Carbon 14, that's a mass number. 12.011, that's the atomic mass. Okay? And this comes from the average of all 3 of these mass numbers. You take the average of the mass numbers or the isotopes, that's another way of saying it, you get this number. Okay, so what's this weighted average thing? Well, roughly 99% of all carbon is carbon 12. Roughly 0.9% of all carbon is 13, and roughly 0.1% of all carbon is carbon 14. Okay, so if you were to take 99%, all right, if you were to take 99% of carbon 12, okay, 99% of carbon 12. So if you take 12 times 0.99, all right, I'm going to do it in the calculator here so I get exact numbers, you get 11.88. All right, now if you take 0.9%, so 0.009 times 13, you get 0.117. And if you now take 0.1%, so 0.001 times 14, so 0.001 times 14, you will get 0.001, sorry about that, I had an issue there, you get 0.014. Now, let's add these up. 11.88 plus 0.117 plus 0.014, you get on the dot exactly 12.011 AMUs. Okay, that's the atomic mass. That's the atomic mass. I used the different mass numbers or the different isotopes to get the overall atomic mass. Okay, so why would we do this? Well, because in nature, we have the combination of all 3 of them. If I were to have a handful of carbon, okay, if I had a certain amount of carbon, it is composed of all 3 of these carbons, and it would weigh 12.011 because it's a mixture of all different masses. It's not the mixture of just one, it's not exactly 12. If I had 100% of just isotope carbon 12, how much would it weigh? It would weigh exactly 12 because it's not a mixture of other masses. It's just a mixture of one of them. Okay, if I had 100% of carbon 14, if I had 100% of, let's say, carbon 52, all right, which does not exist, but let's just say it would weigh 52 AMUs, okay, which is almost the same thing as grams, all right. So, but I don't have individual isotopes. I have the mixture of all 3 of them, okay. So because of that, it weighs 12.011 because most of it is carbon 12. So it weighs pretty close to 12, but I have just, if you take this, All right, 0.011 grams of it is these extra 2 isotopes. Okay, here's another example of chlorine. 75.78% of 35. So 35 times the 75.78% plus 24.22% of 37, and you get roughly 35.45. It doesn't come out exact because I changed these numbers just a little bit to make it more obvious. So if you do this, you might get a different number, but this is basically what you're doing, and that's the atomic mass. Atomic mass is made up of the of the mass numbers. Please make sure you understand the difference. You're using the same words, kind of, and they kind of mean the same thing, but they don't. Okay, one is a mass number. It's a number. It's a whole number. Think of this as a mass whole number. It's 12, 13, 14, 52, 35, 37. Atomic mass, 12.01. Here, let's actually go to the next slide. I kind of wanted to show you this periodic table. I believe this is the periodic table you have. Notice I have these masses here, 1.008. That's because we learned that hydrogen has 3 isotopes. It has a hydrogen 1, there's a hydrogen 2, and there's a hydrogen 3. Most of it is hydrogen 1. Very small amounts of it are 2 and 3. Right? That's why it doesn't weigh exactly 1. It's close. I mean, 1.008. I mean, that is that 0.008 is because of these two. Okay, so notice, chlorine 35.4. Notice most of these. I know this is kind of hard to see, but the point is notice most of them are a decimal point. Notice down here, these are actual whole numbers. Okay, so if you look at the RF, it's 261. That says 261. Okay, it's a whole number. So what does that mean to you? All right, that should mean to you that there's only one isotope of RF. There's only one isotope of RF. And what's its mass? 261. So if you take 100% of 261, it obviously weighs 261. All right, all the other ones that have the decimal points, those all have more than one isotope, and they're being weighted into the mass. All right, so if I have a certain amount of sulfur, okay, if I have a handful of sulfur, it's going to weigh 32.066 AMUs. It's not going to weigh 36, but there is a 36 isotope for sulfur. There might be a 33 isotope for sulfur, and a 34, and maybe a 31, but they're all different amounts. All right, the percentages are different. Okay, so hopefully this makes sense, and that is it for Chapter 1. Please write down all the questions you have, and we will talk about it in class next time we meet.